Good afternoon, everyone. So today we are going to talk about recycle and bypass, the topic of recycle and bypass. But before we talk about the topic, again, let's recap what we have learned last week. I think last week the most important example or the topic we want to know is extraction and distillation process, right? So I'm sure you understand this, and I want you to be very familiar with this example, so you can get good scores in your final and midterm exam. So we have briefly talked about the recycle. Remember, because this recycle is that MIBK will recycle back to these extractors because we don't want to waste the used MIBK. So it doesn't matter if it's a pure MIBK or with a small portion of the acetone or water, right? So this is one of the example for the recycle. Another example is that we talk about a reactor, and we recycle non-reactive materials back to the reactor, because if you want to have 100% conversion from A to B, it might take days, years, right? But if you just want to have 80% conversion, it might take about 1 minute or 10 minutes, for example. So what you can do is you have a separator instead of spend a lot of time to have a completed reaction. So you can have this recycle, you can have this separator to recycle A and B, and then let the unreactive A species back to the reactor. So this is another example, right? And the third example is that what we have learned is that the air conditioner. The reason is that if you want to have the water, this air conditioner, you know, the air conditioner provides the cold air as well as the low water content air out, right? So there's a pipe in the air conditioner. The pipe will, you will have some waters come out from the pipe, right? So that means you condense the water. So if you, for example, if you want to produce the water with like 1.7% water out from the air conditioner, and then your input is 4% water, and then it doesn't work on this air conditioner because you need to dilute the water content in order to make it become 2.3%, so that you can produce 1.7% water. Otherwise, if you have a 4% water into this air conditioner, you cannot produce 1.7% water out. So this kind of dilute streams, right? You dilute the water content before you go into the air conditioner. Okay, this is a third example for you to understand what's the meaning of the recycle. Okay, so today, let's start from here. Is that the reasons for using recycle? So you already know that to recovering and reuse the unconsumed reactants, right? Like this is MIBK. It can be reactants, or it can be the input streams or species, unconsumed species, right? So this is one of example, MIBK example. And then the second one is dilute a process streams. Remember this air conditioner, you want to dilute a process stream, okay? And the third one is you recover the catalyst. Recover the catalyst, which is expensive materials. We don't have example like this to show you, but I think you understand this, because the catalyst is the one which cannot react with the species, but it will reduce the activating energy, right? It can enhance the reactions. So, but you don't want to waste the catalyst after reaction. You want to recycle this and to use this again and again. Okay, another example is control the process variables capacitance for the heat released. This is another example for energies. Okay, again, we don't have an example here, but you can find that it's our. The fifth one is the circulation of the working fluids. Again, this is heat exchange. So we don't have an example here, but anyway, this is the the reasons for using recycles. So, for example, on Wednesday, if I show the Kahoot, the title of Kahoot is Recycle Stream. I might ask you some of these things why we want to use recycle stream. And you need to give me the answer. Okay? Right. So today we want to do another example for the multiple unit processes for mass balance. So these are the evaporation, boiling, and filtration. So before we really talk about the example 4.5-2, evaporative crystallization process, we will need, I want to introduce you evaporator or evaporation first, and then I will introduce you crystallization or crystallizer. And then these two are the unit operation. You will learn when you are in the second year in the chemical engineering department. But I just want to give you roughly idea what's the definition of evaporation. So evaporation is a type of vaporization of a liquid that occurred only on the surface of a liquid. The other type of vaporization is boiling. That is instead occurs on the entire mass of the liquid. So here, the key is that you need to distinguish what is evaporation, what is boiling. So what's the difference between the boiling and the vaporization? Assume you have a pot of water, okay, and you heat this pot of water up. So once you open the fire, you turn on the fire, and then the temperature of the water increase from 25 Celsius, for example, at room temperature, and the temperature goes up. And before it boils, you will see some of the steam come out, right? So this is what we call evaporation. So the water's molecules vaporize from the surface of the water. Okay, only from the surface. Okay, so this is what we call evaporation. But once time goes by, and the temperature in the water is going up from 80 to 100, for example, and it starts to boil. The water starts to boil, right? And you can see a lot of bubbles from the inside of the water. So why is this? Because the temperature of the water reached 100 Celsius. It reached the boiling point of the water. So this boiling is that the vaporization occurred in entire mass of the liquid. Okay? So what is the evaporation? This is the process by which molecules in a liquid state spontaneously become gases. So liquid molecule of the water from liquid state become gas. So what's the difference between vaporization and boiling? Evaporation is surface of liquid, right? The molecules escape from the liquid from the surface. And then the boiling is entire mass of liquid. Okay, so this is the example showing you this. Evaporation is the water molecule come out from the surface of the water, but boiling is that the water vapor come out from the inside. It become bubble, right? What's the bubble here? It's full of the gases, H2O, right? It come out. So of course the vaporization rate of the boiling is much faster than evaporation, right? Right. So this is the differences between evaporation and boiling. Of course, this is the one you use at home. This is the batch process. How about a continuous process? You want to do it in the industrial scale. You want to vaporize water in very fast speed. So we use what? We use a continuous process. So these 5 are the examples of the evaporators. You can, including natural circulation evaporator, forced circulation evaporator, falling film evaporators. There are many types of evaporators, depends on the different application you use. So here I just introduce you one of the example, which is falling film evaporator. So this is what we call falling film evaporator. What's the falling film evaporator? So you have liquids on the top. It's product inlet. So you pour the liquids on the top, and there are some small pipes from the top to the bottom here. Okay, so you have, for example, you have 100 small pipes. So this liquid will drop and go into these small pipes. And then surrounding these small pipes is a stream heater. You use stream to heat this pipe. So once the temperature of the liquid increase, the vapor will be generated, right? Vapor will be generated. So the vapor generated, and then vapor will come out from here. And because you reach some certain temperatures, some of liquid will drop. So you do the separation. Okay, so this is what we call falling film evaporator, because this water only drop from the like a films inside the pipe. So I have some video show you here, so I think it will be easier for you to understand why I'm not like you do it at home. Okay, so this is called evaporator. Okay, so this example involves two unit operation. One is called evaporator. The second one is called crystallizer, or we call filtration. When you are in high school, you do a filtration in a chemistry laboratory, right? So this is a beaker, and you have liquid, and you pour in the liquids, and if you have a pump, you suck the air from this beaker, and then this is called vacuum filtration, which make the process faster, right? So you suck the air, so there's a driving force from the top to the bottom, so the liquid and the solid will drop through this, and you have a filter here. You have a filter, so you can separate solid and liquid, right? So the bigger size of the solid will be blocked in the filter, and the filtrate, some like water or small molecules will drop, and then in the end you come to this bottom. So this is what we call crystallization. We do the separation of this using this filtration process. So the definition of filtration process is that is a mechanical or physical operation which is used for the separation of the solid from fluids. It can be gas, it can be liquid, okay, by imposing the medium through which only the fluids can be passed. So this is called solid liquid separation or solid gas separation. Okay? Again, you do this in the laboratory, but you cannot use this in the industry. This is too slow. This is too slow. So you need to design a process to make this more efficient and to make it continuously, right? So you can make a good products. So this is one of the example called rotary vacuum drum filter. Instead of using this filtration in a laboratory, this is a human being. As you can see, this is the size, which is much bigger than a room like this. Okay, so this is called rotary vacuum drum filter. So the cross section of this filter looks like this. So you have filtration zone. You have liquid and solid here. Okay, you pour liquid and solid in the bottom. So this is the filtration zone. We call slurry. Slurry is is a combination of liquid and solid. Okay? And then this is filter. This is filter. Filter is all around here. You know, the dashed line here represent a filter. Filter. Okay, it can be a membrane or it can be a cloth. It can be a polymer, for example. Okay, and then in the central duct, you have a vacuum. You suck all the airs from the surrounding environment. So this suction will go to the center. And because of suction, the air, this vapor pressure will goes up, and then vapor will go in. So, and then you generate cake here. You generate cake. As you can see, this one will be sucked into here and then block in the filter. So water will penetrate to this filter and go to this duct. Okay, and then you do the rotary. This drum will move. So as you can see, the cake, that's what we call cake. Okay, the cake which is solid. The cake will increase. The size, the amount of the cake will increase, and become thicker and thicker. And because you don't want to have some of the chemicals, so you can wash the cake. And again, from here, dewatering zones, because the suction, the water will go in. Okay, and you have a blender. You have a knife here and cut the solid product, and you get solid product here. Okay. So as you can see, you can get powder-like, but still wet. Okay. So this is called cake. So this is industrial process, which you might need to learn about this, how to design this drum, what's the size, what's the concentration of the slurry, okay, what's the speed, what's the pressure, okay, vacuum pressure. Again, I have a video for you to see how it looks like. This is a very small scale, of course. Okay, easy, right? But again, it depends on different applications. You need to design different rotary drum vacuum filter. Okay? So let's go to the example 4.5-2. That's in your page what? I hope you have the book with me. The page 104, example 4.5-2. I want you to work with me because it will be easier for you when you do your midterm exam if you work with me now. Right, okay, let's, before we really talk about this is a kind of example. Let's see the PowerPoint first. Here, slide first. First of all, you have an evaporator, and you have a crystallizer and filter. So the evaporator is look like this, for example, and filtration filter is like this. So you have this, and you don't need to draw the picture like this, but you need to have a box and tell people that this is an evaporator, this is a crystallizer or filter. So this is an example of the potassium chromate. Potassium chromate mixed with water, And you want to separate potassium chromate from water. So there are two species only, potassium chromate and water, which is slurry, right? So the feed solution here is that you feed the solution and then you do the separation. The evaporator come out with water, right? Come out with water here. And you got slurry. You got slurry, which is the concentration of water here is much higher than here. Slurry means what? Ni in Chinese, right? Ni. Okay. And then if you have slurry and you go to the crystallizer filter process, so you have potassium chromate, which is filter cake. Remember filter cake? Filter cake is what? Because it's still wet. It's not 100% dry. So potassium chromate plus solution. You have solution here, which is what? Potassium chromate solute in the water. Right? Because if you reduce the water in the solution, the potassium chromate will become solid. Right? So it was liquid here and it becomes solid in the end. And then because of this filtration cake, the filter will produce water, will produce solution out, remember? So you have this is called filtrate. Filtrate will recycle back to this place because you still have some potassium chromate. Right? So this is a filtrate. Filtrate from here, remember? Okay? And you have recycle. And then, okay, so this is the process of the evaporative crystallization process. Right, so now I want you to work with me and let's read the sentences and then we write down all the informations we know in this flow chart. Okay, do you have the PDF file or do you print out as a piece of paper or do you have a book with you? Okay, let's do it together. Right, the page 104, a flow chart of a steady state process. When you see steady state, what does that mean? If you think of the general balance equation, if you think of the steady state, what does that mean? The accumulation equal to 0, right? If it's not steady state, the accumulation won't be 0, right? Okay, and okay, a flow chart of a steady state process to recover crystalline potassium chromate from aqueous solutions of this sort is shown below. So you just do a pure separation, there is nothing involved chemical reaction. So in the general balance equation, you can remove the terms of generation and consumption. Right? So the general balance equation will become input equal to output. As simple as that. Okay, so as you can see, the flow chart will, as you can see the flow chart here. So let's read the second paragraph. 4,500 kilograms per hour of the solution, that is 1/3 of potassium chromate by mass, is joined by a recycle string containing 36.4% potassium chromate. Well, this is too long. Okay, let's write down 45,000 kilograms per hour of the solution. Okay, please take a look of this the slides on the in the front. 45 kilograms per hour. This is the feed solution, right? And then by mass, so you know that. And 1/3 of potassium chromate by mass is joined by the recycled strings containing 36.4% potassium chromate. So what is this? This is what we call specification, right? So this is specification. You will have one more equation when you do DOF analysis, degree of freedom analysis, right? Okay, let's remember this. But excuse me. But you can write down here. You can write down here. So this is 1/3, right? 1/3 when you have 4,500, you have 1/3 of potassium chromate. Of course, the rest of them are water, right? However, it's joined by a 36.4% potassium chromate. So we can, so you think this is the 36.4% of the potassium chromate. So this part is what? If you don't think of this is the specification, this is a 63.6% water and then 36% potassium chromate. So this is the one. Okay. And the second paragraph, the line 2 is in the middle of line 2. Let's read that the combined stream is fed to an evaporator. So that's why you say that the combined stream, which is the recycle stream and the feed stream, is joined to feed to the evaporator, right here. Okay. Okay. The end of the second paragraph, line 2, is that the concentrate stream leaving the evaporator contain 49% potassium chromate. So the concentrate stream leaving the evaporator. So the concentrate is that it means slurry, right? So when you take a look of the slide here, this is what? This is the information that tell us that 49.4% potassium chromate here, which is in the slurry. Okay, line 3, 49.4% right down here. Okay, in the middle of the line 3, the stream is fed to a crystallizer in which it is cooled, causing crystals of the potassium chromate to come out of the solution. So temperature will drop in the crystallizer, and then we do the filtration. Okay, in the line 4, in the middle of line 4, and then filtered, right? Okay, remember the line 4, in the end of line 4, the wet filter cake. So the wet filter cake here, this is a wet filter cake. As you can see, well, you might say, well, Professor, the flow chart here is just one stream. Why you draw two streams here? Well, I just want to tell you that this is easier to understand. This is a dry stream, this is a wet stream. Although it's only one, because this stream is a cake, right? Cake contains solid and liquid. Liquid is a saturated potassium chromate solution. Okay? So as you can see this, I want to make this clear to you, so that's why I draw two streams here. But anyway, if you want to draw one stream, that's okay. Okay, so the second paragraph and line 4, the line 4 at the end of line 4, the wet filter cake consists of the potassium chromate crystal, right? So this is a potassium chromate crystal, and the solutions that contain 36.4% potassium chromate, which is saturated potassium chromate. So as you can see here is that potassium chromate crystal, this is crystal. So you have 100% crystal, and you have solution, which is potassium chromate plus water on the slide here. That's why I want to make it clear. So this is pure solid in this stream. Okay? Of course, this is only one stream, but this I want to make it clear anyway. So this solution, which is saturated, and they tell us this 36.4% kilogram potassium, 36.4% potassium chromate. And please remember, because this is saturated solution, which is the same as this. So as you can see, the fraction of the potassium chromate in this stream is the same as the fraction of the potassium in this stream, which is 36.4%. Why? Because this is saturated solution. Okay? And potassium is saturated in this solution. So that's why the fraction in this stream And the fraction of the potassium chromate in this stream is the same as the fraction of the potassium in this stream. Okay, right, let's go to the line, second paragraph, line 5. In the end of line 5, the crystal contain for, the crystal count for 95% of the total mass of the filter cake. So what does that mean? This is the specification, which is what? The potassium, this is something to do with this and this, right? So let's think of this is the filter cake, right? The total potassium chromate is 95%. Okay, 95%. So this is a specification. Let's think of one of specification between these two streams. Okay, right. And then let's go to the last line. The solution that passes through the filter also 36.4% potassium chromate in the recycled stream. We already know this on the slide. Okay? Right. So these are all information we know, and we write down most of the information in this flow chart. Okay, in this slide, so please work with me now. We have one specification which is related to this stream and this stream. Okay, but at this moment we don't write down, but you know, you want to know we have one specification here. Okay, so now let's start to write unknowns to each streams. Okay, the first one is here. So you have a joint point from fish solution and also from a filtrate. So you have one M1 here, which is total amount of this and this. Okay, and of course you want to write down the fraction. So the fraction is X1, which is potassium chromate, which is X1, and 1 minus X1 will be water. Okay, so you complete information in this stream, and now you want to complete information in this stream. So this is pure liquid. You don't have fraction, so you write down M2, which is water only. Okay, and next stream is here. So you have information of the fraction for the potassium chromate and water. So now what you need to know is write down the unknown of the total mass. Okay? Okay, next. So we complete the information of this stream, and now let's go to this stream. So potassium chromate, this is pure solid, right? So you just write down M4. And this solid, this solution, you have potassium chromate, and the water, you have fraction, so you write M5. So you complete information here too. And this will be, and only one left, this will be M6. M6. So these are all the information you know and you don't know. Okay, so how many unknowns? 1, 2, 3, 4, 5, 6, 7. There are 7 unknowns. So let's make small. Let's make it small, and let's do DOF. So you have, remember that 9 steps. The first step is, step 1 is what? Choose the basis. We already have basis. Second, draw the flow chart and label knowns and unknowns. Right, unknowns. So you have 7 unknowns. Okay, so now let's do DOF. So this is the DOF. Let's do overall system. Overall system. Overall system is what? How many input and how many input stream and how many output stream? Please tell me. How many input stream and how many output stream? one input stream and 3 output streams, right? Right? One input stream and 3 output streams. How many unknowns? How many unknowns? You have to think of outside of the box. You have to think of the unknowns outside of the box. How many unknowns? 3, right? M2, M4, and M5. Okay, so you have 3 unknowns. And then you have how many species? Remember, we need to think of how many equations we can have by 4 directions. The first direction is how many species in this system? 2 species, right? Potassium chromate and water. So you can create 2 equations, which is water input equal to water output, potassium chromate input equal to output potassium chromate output, right? I hope you already practice during the weekend, which I don't believe, but anyway, I hope you do. You did. Okay, so and then you know the first direction. How about the second direction? Do you have specification? Yes, you do. You think that we already have specification related to M4 and M5, right? Remember? Okay, so you can have one specification, which is this plus this times 95% equal to this, because this contains 95%. Potassium chromate is about 95%. Sorry. Okay. So do you have physical laws and physical constraints? No, you don't. Okay, because there is no volume, moles or kilograms. No, you don't have the moles or the kilograms. You need to do the conversion or what? Okay, but anyway, you already have enough equations. 3 unknowns. You have 3 equations, so you can determine M2, M4, and M5. Please do this at home. I don't want to waste your time here. This is very easy. So, good news is that you already get this. You see that it was red, right? And now it become blue. Blue means you solve the equation and you get an answer. Okay? Right. So now you got this, you already know these 3 unknowns. Now let's go, because you already use overall, and then now let's go to the single unit system. Let's go to the first one first, mixing point. Mixing point. So mixing point, you have 3 unknowns. How many input and how many output? 2 input and 1 output, right? 2 input and 1 output. How many unknowns outside the box? 3 unknowns, M1, X1, and M6. So you have 3 unknowns. How many equations you can create? You have 2 species, so you can have 2 balances, which is potassium chromate and water. Do we have specification, physical laws, and physical constraints here? No. According to the example, the sentences, you already know there's only 1 specification here, right? And there's no physical laws and physical constraints. So, unfortunately, you cannot use this mixing point to get the answer of M1, X1, and M6. Okay? Right. So, that's okay. So let's move to evaporator. Because let's do it one by one systematically. Let's do evaporator. How many input and how many output streams? 1 input stream and 2 output streams. Right? Okay? Well, how many unknowns? Outside the box, 1, 2, 3. M1, X1, and M3. Again, intuitionally, you tell yourself, wow, you have 3 unknowns. Probably you just have 2 equations. So you cannot solve this problem. You cannot get the answer of M1, X1, and M3. Okay, so let's move to, so you finish this, let's go to this crystallizer and filter. So you have how many input streams? 1 input streams, and how many output streams? 3 output streams, right? So you, how many unknowns? 1, 2, outside the box. 1, 2. So you have M3 and unknowns of M3 and M6. Well, you got a feeling. Yes, I can get an answer of M3 and M6 according to input equal to output of the water and the potassium chromate. Bingo. So you can change this M3 and M6 from red color to blue color, right? Okay? Yes. Wonderful. And then now there are only 2 unknowns here, so you can use this and you can use this to get these 2. Right? So evaporator or mixing point, you can get these 2. 2 equations, 2 unknowns, 2 equations. Okay? So you do the calculation, please. I don't want to waste your time, and please go home and practice this example. So why we want to do this? What's the potassium chromate? Potassium chromate is a kind of dye. You know, it's kind of yellow color. So if your clothes need yellow color, you use this potassium chromate. So it's used as a moderate in dyeing fabrics, as a tanning agent in the lasers industry. So you can have there are many applications. Or you can use these kind of oxidation agents in organic synthesis. However, you want to recycle this. You don't want to put these solutions. You don't want to, when you finish using this, you want to recycle it because it's toxic. You don't want to discharge this toxic solution to the water, right? Let the fish die, and to get river contaminated. Okay, so you want to recycle it, and you save money, right? Okay, so these are the example of the recycle. I hope you practice more, and you know just input equal to output. It's nothing more than this. Right. So next topic is called bypass. But before we move to the topic, before we talk about the topic of the bypass, let's refresh. 希望你都答对了。Okay. So now let's go to the next topic, which is bypass. What is bypass? Remember recycle. This is a process. If I have a feed, this is a feed stream, right? This is a product stream, for example. And recycle is this the arrow go back to this and go to this joint point, right? Recycle back to this before this process. But bypass is another way around, which is not go back to this, but instead it's called splitting point. Splitting point before the process, and you go to the end and come out with the product. Why we need this process? Why we need this stream? Why? It must have some reason, right? Must have some reason. And this is the class you need to learn the reason. So bypass, the definition of the bypass is a fraction of the feed, a fraction, okay? It's not all. A fraction of the feed to this process unit is diverted around the unit and combined with the output streams from the unit. Okay, very precisely, you understand exactly what's this bypass. So why? Okay, why? Let's, one reason I want to show you this is, I will tell you the reasons, okay, in the following slides. But when we do the calculation, input equal to output, the bypass recycle circulation are approached in exactly the same manner. So this is a joint point. Right? So this is a splitting point. This is joint point. So when you do the recycle, this is a joint point, this is splitting point. So when you do the splitting point, that means what? The fraction will be exactly the same. The fraction of the feed stream and the splitting, the bypass stream, the fraction will be the same. Right? Remember that? Okay, so you have, here you have what? One input, you have two input and one output. Here you have what? Two input and one output. Okay? So this is a reason of bypass. As you can see, this is the bypass. So the fluid comes from left and goes through this device and come out, and this is some of the fluid come out to this place. So this is what we call bypass. This is what we call bypass. So there are some reasons. One of these reasons is that you want to fix this broken. This has a problem, so you want to fix this, so you have a bypass. Right? Okay. So there are some examples I'm going to show you. The concentrated juice, mass flow controller, and the jet engine. I don't have time to introduce mass flow controller here, but you will learn this when you are in the college or when you go to the graduate school. Remember, when we talk about rotameter, that's the volumetric flow rate meter, right? So do you have, and how do you measure the mass flow rate meter? By changing the volumetric fluid flow rate meter changed, volumetric flow rate changed to mass flow rate by what? By density, right? But there's a device which you can measure the mass flow rate directly instead of using volumetric flow rate first. So this is called mass flow rate, mass flow controller. Anyway, I don't have time to talk about this, but let's introduce the first example. So this is a bypass. You know, when you go to supermarket and you want to buy a can of juice, and the juice say that's 100% juice from United States. Do you believe this? They will ship this bottle. They will ship this to Taiwan from United States or from Japan. No, it's too heavy. Otherwise, it's too. If they do it in this way, that will be very expensive. Very expensive. Like when you drink Coca-Cola, the Coca-Cola, they don't ship Coca-Cola from United, because the recipe of Coca-Cola, there's only 3 people knows. Well, less than 5. The recipe of Coca-Cola is a kind of confidential secret. Okay, nobody knows, but they don't ship the Coca-Cola from United States to Taiwan. No. Why? They use concentrated Coca-Cola and then they dilute in Taiwan. Or they do another, they pack it in Taiwan. The same as juice. Okay, but however, they use concentrated juice from United States and ship to Taiwan, and they dilute. But they'll find something, because once they vaporize water from the fresh juice, they also vaporize some of small molecules, which is the smell very good molecules or smell very good flavors. Okay, but once you lose this flavor, it will have flat taste. So volatile constituent will be vaporized together with water. Okay, and you lose this. You lose this, but you want to put it back. Otherwise, when you drink orange juice from United States, it doesn't taste like orange juice. You must feel, wow, this is some kind of artificial or orange juice or what. So they put a fresh orange juice back, and you can have the same taste. Okay, that's the meaning of bypass. Let me show you this. So what's that? They have harvested the juice, orange, okay, and they squeeze squeeze the orange and the juice come out. And then, for example, this is United States. And then you want to, and they don't want to ship this heavy, they contain about 95% water. So you don't want to ship water from United States to Taiwan, right? So you need to concentrate, you need to vaporize most of the water. So you have a concentrated juice. And you ship from, the juice, the concentrated juice was coming from the United States by boat, right? And then to Taiwan, and then you dilute. You put the water into this concentrated juice, and because you want to have the same flavor, same taste, so you have some of the you have some fresh juice also, and put it into this dilute juice. So, and then they do the package, so you can have the same drink. You don't tell the differences. Okay, this is where is the bypass? This is the route, right, from the harvest, from the United States, and the shipping by boat and to Taiwan, for example. So this is the bypass. It doesn't go, you have squeezed orange, and you got juice, fresh juice, and this is the bypass going to the end. Okay? So this is the orange juice production. You know, I just show you a tomato juice. The same thing like this, right? So this is example 1. Example 2 is a turbine fan engine. You know, this is the engine. Why airplane can fly? Because there's a combustion between oil and air, right? And oxygen, and they generate, the oil and the oxygen generate huge gases, and then gas push this air flight to move forward, to move, right? So that you have a strong power to move this. So once the air was sucked into this engine, and then oil combined with air, and then they just have a chemical combustion, right? Combustion, and the huge amount of the gases come out. However, this kind of process make huge noise, and then you cannot bear this kind of noise. So there's a byproduct air, bypass air. It doesn't go through this engine, it goes through surrounding the engine. So you have a hot air and cold air. Hot air here and cold air here. So it can reduce the noise. So this is another example of bypass. So this air doesn't have chemical reaction with oil. Instead, the bypass goes through this process. Okay, this is another example of bypass. Another one is artery bypass surgery. So this is not your heart, okay? This is the patient's heart, and this pipe, this vessel, this artery was blocked, and your blood cannot go through this. You are going to have a great danger. No, not you. I mean, the patient is going to have great danger. So you need to have a bypass to let the blood go through this path instead of here. Of course, you have some of the blood go through this because it's not 100% blocked. Right? So this is what we call bypass. Bypass. And you need to do input equal to output, right? Okay. Right. So his summary is that I think just the splitting point, important is splitting point. This is the same fraction. Okay. So I hope you understand there are two streams you need to learn. One is bypass, one is recycle. And you need to know the reason of the recycle stream and the reason of the bypass stream. Okay, so this is the reaction. So how do you do mass balance in chemical reaction? Now will be in 4.7, but before that, let's go back to our high school and start to to recap what we have learned about chemical reaction. So 4.6 chemical reaction stoichiometry. So again, this is a reactor, right? This is reactor. And A will become B. So A in and B out. Of course, if we don't have enough title for the chemical reactions, you might release some of the A reactant out. So you might have A and B. So as a result, input equal to output, you will have what? You will generate B, right? And you will consume some A. And if this is a steady state, you have a term here which is accumulation. But if this is a steady state process, accumulation will also equal to 0. Okay? Okay, let's go to 4.6a, stoichiometry. What is stoichiometry? For example, if you have two species, A and B plus becomes C and D. But again, you will have some A and B in the output stream. So stoichiometry is a theory of the proportions in which chemical species combine with one another. I'm sure you all know this already. So the measuring chemicals that go in and come out of any given reaction. In Greek, means measuring elements. So stoichiometry means measuring elements. So element need to be exactly input equal to output. Okay? So this is kind of studies. Stoichiometry is a kind of study. So what is stoichiometric equation? So stoichiometric equation is a statement of the relative numbers of the molecules or moles of the reactant and products that participate in the reaction. Okay, there's a Chinese here, so I'm sure you understand. So for example, you have 2 more of the sulfur oxide become plus with oxygen become 2 sulfur SO3. Okay, so you know the oxygen, I'm sure you know that the numbers of the oxygen element on the left hand side should be equal to the numbers of the oxygen element in the right hand side. The same as sulfur, right? Okay, this is what we call stoichiometric equation, and then stoichiometric coefficient. This is a stoichiometric coefficient. So 2 more, these 2, and 2 more here, and 1 here. So the oxygen atoms on the left equal to oxygen atoms on the right. How about stoichiometric ratio? Stoichiometric ratio is what? Stoichiometric ratio is, this is 2 moles, this is 1, right? So if I say, well, please tell me the stoichiometric ratio of the sulfur oxide to oxygen, that will be what? 2 to 1. So for example, SO3 to O2, that will be what? 2, 1, right? That will be 2 more. That will be 2. Ratio will be 2, which is dimensionless quantity. How about SO2 to SO3? SO2 to SO3, that will be 1. Right? Easy. Piece of cake. Right, so now I give you an example. Stoichiometric equation, this is stoichiometric equation. Right? So you have 1,600 kilograms per hour, SO3 is to be produced. So you are expected, this was expected to produce 1,600 kilograms per hour. So I want you to know, I want you to calculate the amount of the oxygen required. I'm sure you can do this. This is junior high school level questions, right? So please do this by yourself. But important thing is that if you can do the dimension, you can solve this equation by dimensionless equation. You upgrade to college level from junior high school level. Okay. So this stoichiometric ratio. This is dimensional. This is a dimensional equation, right? This is conversion factor. Remember, this is called conversion factor, which is applied to the chemical reaction. This is stoichiometric ratio. Okay. So let me summarize this, what we learned, stoichiometry. So this is what we call the study of, this is kind of theory. This is a theory of stoichiometry, and this is what we call stoichiometric coefficient. Okay, coefficient here, coefficient here. If we think of the ratio, if this and this together, if you want to know the ratio, the mole ratio, this is 2, 1, 2. This is called ratio. And if we put it together, this is called stoichiometric equation. And this kind of study is called stoichiometry. Okay, so now stoichiometric coefficient, stoichiometric ratio, and stoichiometric equation. Okay, these 4 terms. Right. So now the example, the section 4.6b, we want to learn another 4 terms, which is the A is limited reactant, B is excess reactant, C is fractional conversion, D is extent of reaction. Okay, let's use this equation, stoichiometric equation, as an example. Okay? Okay, the first one, limited reactant and excess reactant. When you see this reaction, which one you think it can be a limited reaction, which is more, make the process more economic? You save money. Which one should be excess reactant? Air, right? Air should be, if you want to make a perfect, air should be excess reactant. Why? Because if you pump the air, oxygen will be excess reactant. Why? Because you pump air into this reaction. The air contains 21% more of the oxygen. Okay, so intuitionally, you will think, wow, oxygen should be excess reactant, and SO2, sulfur oxide, will be limited reactant. Why? Because this is reactant. This may be more expensive compared to air, right? Because air is free. So you have input 2 moles of SO2, and here input 1 moles of the O2. So you have 2 moles of the SO3. This idea, right? This idea, but but normally you will have more oxygen into this reaction because you want to have complete reaction. So ratio of input is 2 to 1, right? Is 2, or SO2 divided by O2 will be 2. Okay, so there are 2 circumstances. The first case is if the ratio of the input equal to the stoichiometric ratio, configuration. This is called stoichiometric proportion, which is you fit 2:1 proportion, stoichiometric proportion. This is good. However, if the ratio of the input doesn't equal to the stoichiometric ratio, which is not 2, so limited reactant will use up first. In the case, we want to use up this O2 first, SO2 first, right? So this will be limited reactant. And this will be excess reactant in this case. Okay? Right. So the term fractional excess, which is if you have excess reactant, right? You want to know how much more. You might want to have 10% or 20% excess, or we call this fractional excess, 20% or 10%, or 100% if you like. It can be, right? So for the excess reactant, for the fractional excess, A will be, please remember this equation. This is easy. It might be in your Kahoot next week. The A fit minus A stoichiometric divided by A stoichiometric. For example, in this case, this is 1 mole, right? If I have 2 moles and 1 mole, if I give you 2 moles of the O2, so what's the fractional excess? 0.5. Easy, right? If you have 2 moles and 1 mole, if SO2 is 2 moles, and I have 2 moles of oxygen, so what's the fractional excess? 0.5. Answer, 0.5. No? No, please. This is very easy. Again, I want to give you this point. I desperately want to give you this point. If I have 2 moles of SO2 and I have 2 moles of oxygen, what's the fractional excess of the oxygen? No? So this is fit, and this stoichiometry divided by stoichiometry. What's that? 2 minus 1 divided by what? 1. So the answer is 100%. Right? Right? Are you with me? Are you with me? I'm sorry about this. I don't know why you don't get the right answer. But anyway, this is very easy. Okay, this might be in your Kahoot next week. Okay, so if I have 1.5 oxygen fit minus 1.0 oxygen stoichiometry divided by what? 1.0 oxygen stoichiometry, that will be what? The fractional excess will be what? The fractional excess will be 50%. Piece of cake. Okay, so what? Do we have time now? Oh no, we run out of our time. Okay, I leave this to you. We will talk about this on Wednesday. So I really hope you learned something in this lecture. Otherwise, there's no point you come here, right? Okay, you go home and do practice. Most importantly, I hope you enjoy the lecture.